love it when Donald's here. You can tell he's hanging out, probably wanting to talk to Dr. Ray Martin while he's waiting. He has to busy himself. And I love the fact that he's giving my suggestion, health and yeah, notice the arrangement of the erasers too. Flanking the pen. Okay, getting back to GRB. GRB2 actually has one SH domain. SH domain. And two, SH3. Okay, and I had it the other way around. I had it, I think I described that it was two SH2 domains and one SH2 domain. Other way around. So I found this online, and I like I've been looking at this. It's a list of proteins that are involved in receptor tyrosine kinase signaling, and all of the domains. GRB2 is actually the simplest of all of them because it is just an adaptive protein. So, did you get it? Did you get it, Dina?
Yep, it's all good.
Okay, okay. Carly, can you hit, did you hit
It's
the record?
recording.
Oh. Did it record when I was saying something about if it was just Ryan? Ryan, you can ask me later. Okay, so we have a little bit more to go through. And then, so probably Monday, Tuesday. So Monday's going to be the homework, the old homework. Tuesday should be pretty much reviewed. There we go. There we go. Okay, and today we're going to cover the JAK-STAT function.
You said you wanted to finish the rest.
Oh, yeah, I should finish the receptor tyrosine kinase and getting rid of RAS. Okay. There is, because RAS has awful GTPase activity inherent, it will not hydrolyze its GTPase or GTP very efficiently. So the other thing that has to bind to the receptor tyrosine kinase is a RAS gap, and it is called RAS gap, which is one of the clearer names for a protein. The RAS gap has an SH2 domain that can bring the RAS gap up to the cell membrane where RAS is located. Okay, so it can then activate the GTPase activity of RAS. Okay, so just remember, the RAS gap does not hydrolyze the GTP for RAS. RAS has to do it itself, but the gap certainly enhances the activity. The RAS gap also has an has a plexin homology domain, so it could bind to PIP3. I don't know if it does, but it has the potential to bind to PIP3. In fact, a lot of the proteins that have SH2 domains, that normally bind to receptor tyrosine kinase also have plexin homology domains, so they can be docked onto the cell membrane a variety of different ways. Okay, so that's RAS-GAP. Definitely essential. Okay, JAK-STAT pathways. Are those pathways in which the receptor just has a receptor binding domain and the transmembrane domain, and they have to recruit a JAK. So the tyrosine kinase activity is really done by JAK. And JAK becomes tau phosphorylated, and so does the receptor. Okay, so when a ligand is bound, and then we'll talk about various ligands.
So is it JAK phosphorylating it?
Yeah, yes, so you could say it autotransphosphorylase. Okay, all of the ligands that bind to the JAK-STAT receptors really are things that would, they tend to be things that would activate immune cells. But there's some other examples too. So here are some example ligands. Erythropoietin. I might have it spelled correctly here. Let me see if I can. Yeah. Okay, to stimulate myeloid cells into red blood cells. Or if you use interleukins, okay, myeloid cells can become white blood cells, almost all kind of white blood cells except lymphocytes. Okay, so the exception is the cells that we work with in the biochem lab are not going to differentiate at all. In fact, the cells that we work with in the biochem lab need neither interleukins or erythropoietin. And that kind of bothers me a little bit in doing the experiments, but it sure is cheap and easy to grow. Okay, interferons. Okay, sometimes the interferons establish an antiviral state in the cell. Okay, and I think that's gamma. Nope, it's alpha. Okay. Okay, or they can activate macrophages. And that's interferon gamma. Okay, so these are clearly involving blood cells, or things that could become lymphocytes or activate the immune system. But then you have something like growth factor, which is or a growth hormone. I'm sorry, not growth factor, growth hormone. was gonna say, man, that sounds like a whole bunch of things from the pituitary gland. That will also bind to a JAK pathway. And prolactin, which stimulates milk production. Okay. So various cells have different kinds of stats. All of these are JAK's main job is to activate a transcription factor called STAT. Okay, and there's, I don't know, about 5 different kinds of stats, maybe more, but each tissue type produces a different kind of stat. So the myeloid cells that we are using in the biochem lab would actually activate STAT5 or use STAT5 if you were stimulating the cells with erythropoietin or interleukins. Okay? All right, so we're going to get to, so stats are, I'm going to try to draw this in the wrong way. Okay, so this is a stat. It has an SH2 domain, and we're going to pull in 2 stats here. Okay, so in the activation domain of the transcription factor, in other words, a big bulb, I put an SH2 domain because that's what gets it up, that's the thing that gets the stat up to JAK. And then that little finger or ear is the place where JAK is going to phosphorylate. Okay, so it's really tough to draw, and it's going to get even tougher. Okay, you got that part? Okay, an SH2 domain here, and this little finger is going to get phosphorylated. Once the stat becomes phosphorylated, it's called if we're thinking about being in the membrane. Or if we're thinking about being in a myeloid cell, whether it gets activated by erythropoietin or interleukins. Okay, so once the stats become phosphorylated, they release from the hormone receptor. Okay, and they dimerize because they're going to use. Okay, here's the tricky part. They're going to use their SH2 domains. Oops. Okay, there's one, and then okay, so the stats dimerize. Okay, so they use their SH2 domains to bind to each other through the tyrosine phosphate that JAK put on. Okay, and at this point, they ought to be going to the nucleus so they can turn on some genes. Stats have a nuclear localization signal. So let's see, so far we know that stats have a SH2 domain. Okay, also a place for tyrosine phosphorylation. They have a nuclear localization signal, Okay, so that would direct the transcription factor to the nucleus, but they don't use it. I don't know why, I don't know if it's concealed or what. So this is a nuclear localization signal. That remains unused, okay? So in other words, they have to have a different way of getting into the nucleus of the cell, and as a matter of fact, they do. And it's a crazy strategy. Okay, we'll try blue. And it involves a small protein called RAC. Okay, so we've mentioned RAC in the biochem lab because it's a GTP protein. It's a G protein kind of like RAB, kind of like RAS. It has a prenyl group, okay, like RAS, okay? So RAS, if you can think of, I'm going to draw RAS over here. RAS has a farnesyl, okay? RAC has a geranyl-geranyl group, so this prenyl group is called geranyl-geranyl. Because it's made up of two geranyl groups linked together to make one big, long prenyl group. That is involved, okay? And I'm going to change the picture just a little bit here. But RAC is going to be responsible, be responsible to get the stats into the nucleus, but they can't do it by themselves. So the RAC is going to be attached to its gap. So we'll have RAC gap. This complex. Okay? But that's not enough to get the cell, to get everything to the nucleus. We need yet another protein, which is just becoming crazy. Okay, and the other protein, I'll make it green, okay, is a cargo selector. So things just don't wander through the nuclear pore. They have to be bound to a cargo selector. So this protein called importin is a cargo selector, and what it's selecting is the nuclear localization signal on the RAS gap. RAC gap. RAC gap has a nuclear localization signal also. Okay, so that's the thing that important recognizes. So, in order to get to the nucleus, these guys have to bind. Okay, so the stats, I'm saying stat 5, bind, well, it is in this case, stat binds to RAC gap. Okay, RAC gap binds to important, and that once this whole complex of 1, 2, 3, 4 proteins forms, well, 5, you got to count important. Then it can go to the nucleus. Okay, then RAC hydrolyzes its GTP, and the whole complex falls apart, and the stats, there's the SH2 domain. I'm pretty sure it's still phosphorylated. I don't know what would remove it. They will bind to the DNA to turn on genes for cell division. For example, they will turn on genes for perhaps differentiation, depending on other transcription factors. But anyway, they would turn on a couple sets of of genes, depending on other transcription factors, because usually gene activation is going to require more than just that pair of transcription factors. Okay, so stats, let's see, so they have to have a dimerization domain. Let's see, no, they dimerize, let's see, what else? They have to have a RAC or RAC gap binding domain, okay? And I think it's the RAC gap that they're actually binding to. So we'll add it up here. Binding domain. Okay, and even though we say transcription factors activate genes, that's sort of true, but they activate genes by recruiting other proteins that actually do the activation. So in order for stats to turn on these genes, they can't do it by themselves. They have to actually recruit the activators. So, and those activators are called coactivators. And I'm not sure which one stat uses. Okay, but it's the coactivators that actually do the activating. And all the transcription factors do is say bind here. Okay, they select the gene that's going to get turned on or turned off. And it's the cofactors that really do the job. Okay, got it? So far so good? Okay, since this has been the pleasure of the Biochem Lab students to understand how statins might inhibit this process, I thought, well, you guys, the whole class should actually be aware. So now you've got this process, let me talk about statins and how they impact this particular process. Ugh. Okay, I'm gonna do a couple, about Crestor, Lipitor, what else? Huh? What? Zocor, that's it, of course, that's in the statins. Okay. So there's a variety of statins that when the drug companies had a patent on their statin drugs, they were, they could give the statin whatever name. So the first company to develop Crestor called it Crestor, and then Lipitor. Lipitor I think was first, and then Zocor. Okay, these are used to lower serum cholesterol in patients with high serum cholesterol. So my husband takes Zocor. And another name for Zocor is, but the pharmacy doesn't give him Zocor, they give them the generic, which is Simvastatin. And by the way, I read a paper just early, and I think it's actually in the cell biology final paper folder that looks at the different anti-tumor activities of these statins, of all the statins, and Simvastatin still has the best anti-tumor properties. Okay, so all of these lower serum cholesterol by blocking the synthesis of cholesterol in the liver. The liver is the place where almost all of 80% of your cholesterol that's circulating in your bloodstream is made by the liver. So the best way, the most effective way to lower cholesterol is not really through dietary change, although that could help. The best way is just don't make reduce the amount of cholesterol made by the liver. So we start out with a molecule that's attached to coenzyme A, HMG-CoA, and in the process, and don't worry about the structure, it's converted to mevalonic, and the enzyme is HMG-CoA and W. We're going to turn some double-bonded oxygens into hydroxyl groups in the process. And the statins block this reaction. Okay, now, and this is how it works. So we go through a bunch more steps. We get a farnesyl pyrophosphate. So pyrophosphate is just two phosphate groups linked together, okay? And then we keep going and going. A couple more steps later, you get cholesterol. Okay, so that just stops statins clearly stop the production of cholesterol. And it's not uncommon to choose a step early in a biosynthetic pathway, because generally a step early in the biosynthetic pathway is a regulated step. It's a slower step, usually, because that's, but it's also regulated, so it's kind of good to, it's really a good idea to block the regulated step. You don't want to get down here and have a regulated step speed up the synthesis of cholesterol. Okay. Well, it turns out that the farnesyl pyrophosphate can be used for other things. Oh, wait, one of the byproducts is here. I should put a couple arrows. You don't have to write this down. Geranyl pyrophosphate. You get farnesyl pyrophosphate, and then from there you get geranyl pyrophosphate. Okay, so this is a really long prenyl group. This is a sort of long prenyl group, and this is a short prenyl. Okay. Okay, so am I missing anything in the pathway? This turns into dolichol. Okay. And where have you seen the word dolichol? Yeah, that's the dolichol is a really, really long prenyl group on which those oligosaccharides are built in the ER. Okay, so I don't know what effect statins have on the production of the oligosaccharide on ER. Okay. Well, this is usually then attached to RAS, okay, by farnesyl pyrophosphate, or farnesyl transferase. But what happens if you are taking a statin? You're not producing a heck of a lot of farnesyl pyrophosphate. Okay, and the geranyl, and there's the stuff I'm missing. Geranyl pyrophosphate is used for attachment to RAC. So there's a geranyl transferase. Okay, that is used to prenylate RAC. Okay, so if people who are taking statins have less prenylated RAC, they're not making enough geranyl prenyl groups to attach to RAC. So the amount of geranylated RAC goes down, the amount of farnesylated RAC goes down. Okay, and the other protein that you can focus on too, there's another G protein called Rho. Okay? So so people who take statins, if you look at that whole population of people who take statins, they have a lower cancer incidence than people who don't take statins. Okay? Because statins through these other pathways are involved in, and then there's a whole pathway that I just discovered that's even funkier and actually probably more powerful. Okay? But there's a reduction in cancer incidence in people who take statins, and the idea is maybe farnesyl, the RAS isn't getting farnesylated, so you can't activate RAS. Or you don't pull RAS up to the cell membrane where it needs to be active. We're looking in the biochem lab thinking, well, maybe it's really RAC. Okay, because we also know that RAC can't get, RAC is absolutely essential for getting STAT into these myeloid cells. But we're also looking at NF-kappa B and the transcription factor NF-kappa B, who also requires RAC. And NF-kappa B has some we're looking at the anti-apoptotic activity of NF-kappa B, and if you treat cells with simvastatin, can you cut down can you make the cells more sensitive to apoptosis? And the answer is yes, you can. But we're looking at changes in NF-kappa B activity, because RAC is also used to get NF-kappa B into the nucleus, but not by that process, by a different process. So anyway, so we're looking at, statins are sometimes hot topics in cancer research, sometimes not so hot topics in cancer research. They get hot and cold. They're also probably right now the current hot topic for statins is because of the impact on the stats. Okay, you are seeing some it has some pretty strong anti-inflammatory activity, because usually stats turn on inflammation genes. So that's where the research, I think, is pretty hot right now. Is that stats block the activation of stats. Statins block the activation of stats. And so a lot of lymphocytes and other kinds of cells of the immune system aren't being activated. But there's some good cancer stuff going on right now. Okay, JAK-STAT pathways. I want to make sure you understand that all of the proteins that receptor tyrosine kinases can attract, like the phosphatidylinositol kinase, phospholipase C gamma, all of the RAS activation, the GRB2, all of those can happen here too. Okay, I just didn't show it. I just showed specifically RAS. But this receptor complex also can activate, okay, PLC gamma, okay. They can activate PI3 kinase. Okay, I think what I need to do next is teach Donald to not line up the pins that are running out. GRB2. Okay, and then the RAS gap. And whatever, okay? It's just that they have the added feature of attracting and binding to stats, the transcription factors. This is like the shortest signal